Okay, so now let's try the flip side. The flip side is we have to find the test vector for b stuck at 0. We already did a stuck at 0 in the previous video. So for b stuck at 0, our analysis is going to be almost the same. We want to assume that this side, for whatever reason, is stuck at 0. So the fault is somewhere here. I think I should use a red to represent that. So for whatever reason, yeah, stuck at 0. And to test that, we have to make sure that whatever is coming through these gates, I'll call it gate 1. Whatever is coming through these gates, I'll call it gate 1, is 1. Okay, whatever is coming through this gate is 1, so that I can test for the fault. Okay, so this gate produces an output of 1, so that I can test for the fault b stuck at 0. And we are not really fortunate because there isn't much we can do at the inputs. Let me label the inputs just like the previous one. There isn't much we can do at the inputs to really generate the test vectors, because I mean there can be a multiple of ways C and D can give you a 1 at the output. Okay, so let's try the first step and propagate backwards. So we have B here and we have whatever is coming through this point here, we don't know. But let's say we want to propagate the error B forward, right? What it means is that we have to make here to be stuck at 1, or like we have to make sure that whatever is coming through here is 1, or the test vectors we have to generate makes here 1, so that the output will be B. Right, what I'm saying is that this is an AND gate, so this one is an AND gate, right? And an AND gate, it will implement a function such that x times y, that is what it does. Now if we assume that the y is this one, right, and the y is 1, right, then it's x times 1, which is what, x. So it means that our fault is only dependent on the x. That is what we want to do. We want to make sure that the circuit output only depends on the faulty one. Okay, yes, and we've done that. Now what we have to do is that we have to propagate backwards so that we can see the test vectors at the various points. So in order to do that, let's take a look at the gates backwards. Well, the gates here, let me call it G2. It's a NOR gate, right? So it does something like x plus y or bar, not OR gate. Okay, and we want to make it such that it always produces 1. Now, this gate would always produce 1 when x plus y always produces 0, right? So it means that the inputs always have to be 0. So it means that here always has to be 0, here always has to be 0, right? So that this gate will always produce 1, right? To make our test, our feed forward step correct. Then we propagate backwards again, and now we are seeing that this part should always output 0, right? And to always output 0, we have A and B right here, right? And this is a NAND gate, so let me call it G3, right? In a NAND gate, and in a NAND gate, if you always want to output 0 in a NAND gate is what, x, y, or bar. Okay, if you always wish to output 0 in a NAND gate, then it means that both inputs have to be 1, right? Yes, so it means that we have to fix here to 1 and here to 1, so that this NAND gate will always produce a 0. Okay, so we are very fortunate. The backward step seems very consistent, right? We always have to produce a 1 here, always have to produce a 0 here, so it seems very consistent. Now let's do for this gate. So let me call it G4. And this gate also doesn't seem very difficult. It is an AND gate, and already one of the inputs is feeding it 1. Okay, yes, one of the inputs is feeding it 1. Now, since one of the input is always feeding it 1, right? But the truth is that we are supposed to always produce 0. I mean, from gate 2, we realize that we're always supposed to produce 0 here. Okay, so if this one is giving 1, right, so that we produce 0, it's simple. We just make sure that C is always 0. Okay, yes, and I think with that we have generated a test pattern. So it means that when we propagate this 1 backwards, it means that B has to be 0, so that when you invert it you get a 1. Then A always has to be 1, right? Then C always has to be 0, right? And now you realize that we come back to the very crucial step. If C always has to be 0, and such that when it passes through this gate, it produces a 1. Right? This gate is an XOR gate, so it does something like C bar D and C D bar. Right? It does that. So when it does that, you realize that if we are saying that C is always 0, then it means that D has to be always 1. Right? To get a 1 from this whole expression. Right? So D always has to be 1. So it means that our test pattern would be something like 1 0 0 1, right, for testing for the error at B. Okay, and you realize that this is quite similar to what we got for the previous question. For the previous question, we got this test vector to test for A, and the other test vector to test for A was 1 0 1 0. So 2 test vectors. Okay, now assuming that only one of these faults occurs, right, it's this 1010 is more unique to test for A, and this 1001 actually tests for both A and B, right? I've not done the other part, so I'm not really sure that there is this B is also tested for by this vector. Okay, but in any case, realize that this test vector happens to test for both of them. Okay, so it's very necessary to ensure that your test vector are unique, right? So make sure that this one is the one testing for B, right, and probably this one tests for A. Yeah, let's try the Boolean difference method to see if we get a different answer, or at least let's verify our answer. So with the Boolean difference, it says that when we do f of, like, we take the function given that our vector we are looking for or is 0, right? X or f, our vector we are looking for is stuck at 1, right? We should get a 1. Okay, so when we write the Boolean function of the whole circuit, right, I think we wrote it yesterday. Okay, let me get it quickly for us. So our function f is something like this, right? And when we look at the diagram, we realize that our b, or small letter b, is just the output of the XOR function, right? So it means that all of these things here can be represented by b, a small letter b. So we can still have a b bar plus b bar c, all bar multiplying small letter b. Okay, because it's actually the same function and nothing has changed. Okay, now we have to find f of y equals to 0, right? And that is, take the target variable and set it to 0 and put it into the equation. So our target variable is b, right? Because that is what we minimize the equation to. So our target variable is b. Now when you end b with all of this expression, you get 0. So f of y equals to 0 will give you 0. Okay. Then the next one is f of y equals to 1. Right, so set b to 1, and when you end 1 with all this expression, you get the same expression. So f of y when it's equal to 1, you get a b bar all bar plus b bar c. I think all of this expression with a bar. Yes. Now the next step is that you are supposed to find the XOR, right? So you have been able to find this side and this side. So you have to find the XOR of the two. So this is an XOR. It's a plus with a circle. So this is an XOR, right? And when you find the XOR of the two, it should be equal to 1. Now, hope you know the XOR function. When you XOR anything with 0, it will give you the same thing. So when we XOR this whole expression with 0, we'll get the same expression. Okay, so it means that you have to find vectors such that AB bar plus B bar C all bar is equal to 1. So you have to find a vector such that all of this is equal to 1. Okay, yes, and so that's what we are going to do now. Usually what you do is that because this expression has an all bar on top, right, it means that there are some techniques you have to take note of. For example, this B bar C, right, should always give you a 1, right, to ensure that should always give you a 0, right, to ensure that at the end you don't OR it with this one and come and get a 1 and it will be inverted to 0. So this is what I mean. The only way you can get a 0 in an OR gate is when this one is 0, this one is 0, so that after inversion you get a 1. Okay, this is just Boolean logic. So if you want to get a 0 here, it means that you always have to make sure that either when B is 1, right, C will be 0. Okay, and when B is 0, C would also be 0. Okay, so that in both of the cases we always get 0 for this side. Then we have to also work on this one. So on this one, realize that we also always want to get 0, right, for this whole expression, the whole expression under the bigger bar. Now this expression would this big expression will only give you 0 if this smaller expression will give you 1, because there's an inverter on top. Okay, I know it's a bit confusing considering the different levels of abstraction. So this expression is supposed to give you 0, right? This means that this smaller expression is supposed to give you a 1, right? So we have to get it such that when A is 1, right, B is 0, because we want to get a 1. And the second part is we have to get it such that when A is, yes, I think that's the only way, right? In the other cases, when A is 1, still B has to be 0. That's the only way you can get a 1. So those are the possible cases. And you realize that when you insert this, either of this into the equation above, right? So either of these ones into the equation above, you will be able to get a 1, right, at the output. And that's what we have been driving at. You could have used the original method, or you could have used the Boolean difference. So at the end of the day, you realize that this test vector also tests for B stack at 0. So you realize that two test vectors uh, test for two different faults in the circuit. Okay, and that's I think the solution. So any of the two test vectors will test for any of those two faults. Thank you.